Hi there and welcome. This video is describing functions with the words increasing, decreasing, a local maximum, local minimum, and a short introduction to what a critical point is. The chapter 4 topics this week are listed at the top of these lecture notes. I don't do them exactly in the same order that the textbook does because I think that the way people conceptually understand these topics are in a slightly different order. So I'm going to do in the order that I hope makes more sense to folks than just exactly aligned with the textbook. So we're going to be focusing again on increasing, decreasing, local min, local max, and introduction to what a critical point is. All right, let's get going. So the first thing we're going to do is investigate a function, and we're going to talk about important features like peaks and valleys, increasing, decreasing, those sorts of things. So here's my function in example A. It's this x cubed minus 9x squared minus 21x plus 5 function. And certainly we can go and graph it. I've already graphed it right here. So it looks like this sort of U-shaped thing. And that's, fine and dandy. The issue is that using technology to help us find the answers, the keyword here is help. Certainly this can locate a peak if I can get it really closely there at -1 comma 16. But computers aren't very good at exploring and investigating, and that's something that humans are really good at. I mean, we could explore and investigate this picture on Desmos. I could see this as a maximum up here at -1 comma 16. We'll be calling that a local maximum from going forward from chapter 4. And we can look down and see that it doesn't appear to have any minimum. So it appears just to have this one maximum up here at that point. If you're a little bit more investigatory, you may want to zoom out and you can see, oh, actually, the graph comes back up eventually and has another intercept over here somewhere, if we can try to find it. And if I go down really, really far, it does have a valley or a local minimum way, way, way down here. And maybe it has more of these. Maybe if I zoom around more on this graph, I will find more peaks and valleys or intercepts or things like that. What we're trying to do today is not have to worry about guessing and hoping. We're going to use our calculus to know for sure exactly how many peaks and valleys and things like that there are. So that's kind of the idea. Graphing is going to help us, but it's not going to be able to substitute our ability to do math and investigate using the actual calculus. All right, so back to this equation right here. And we're going to be looking at peaks and valleys. We know from the picture it has a peak, and I will parody that right here a little bit. We know that the graph kind of went up at some point. Let me see if I can get it more accurate. It goes up right around there and then back up there. Okay. So I'm just going to I don't even remember what it looks like. That's how bad I am about this. Sorry about this bad video. Yeah, right there. Okay, I was doing it. I just lost confidence. Okay. Goes way down here and back up like there. So we know that there is some sort of peak or local maximum there and a local minimum here. And what I want you to think about is from a calculus perspective, how do we sort of label that or understand that in terms of our equations? The key here is using a derivative. So if we zoom in on this first peak right here, which looks sort of like this in a little zoomed in version, this peak, if you look at the left side of the peak, if you look at points on the graph that are to the left, you might notice that the derivative is always positive. That's because the graph is increasing. Increasing graphs mean that the y value gets bigger, and so the derivative is positive. So here we have the derivative is greater than 0, the graph's going up. And you might also realize that on the right-hand side, if you take any points on the graph over here, the derivative will be negative because the y values are getting smaller. They're getting less and less. They're subtracting, and so less and less. So we have this idea that derivative is positive is increasing, derivative is negative is decreasing. So how do positive numbers or positive derivatives change into negative numbers, right? And the answer is like there has to be a transition, right? This is slope of +2, +1, positive a half, -2, -1, negative half, right? You have different positive values. What happens to the derivative right here in the middle? Yes, the derivative there will be equal to 0. So this is going to be a key idea here, is that if you have increasing and then decreasing in the middle, has to have something very specific. In fact, derivative equaling 0 is the most common thing that will happen between increasing and decreasing. And that's how we're going to find maximums and minimums, local maximums and local minimums. There was another possibility, by the way, of a transition between a positive derivative and a negative derivative. Doesn't happen as often, but you may remember back in chapter 2, we talked about the fact that sometimes graphs come to like a point. They're called a cusp, right? Where it's kind of like a point. I don't know how to describe it, but here we have the derivatives are positive. So if you think about drawing a tangent line, these are all increasing. The graph is clearly increasing. So the derivative here is positive, and likewise, the derivative over here is negative. However, right at this transition point, the derivative doesn't exist, right? At those points, at those cusps, you have the derivative dne, and that's because the limit doesn't exist there. So dy dx equals dne. So there's going to be kind of a couple things we need to look out for. Derivative equaling 0, and occasionally the derivative does not exist. This is supposed to be a dne. And those are going to be eventually labeled. They're going to be given a name. They're going to be called critical points. Those are points in which we have a transition. We have derivative equaling 0, or we have the derivative not existing. Okay, so let's get busy trying to use our calculus to find, for this particular function, those important points. We're going to label increasing, decreasing, and local min, local max. All right, so we do have our function over here, and I'm just going to find a quick derivative without much discussion. Okay, and we need to find out when the derivative is equal to 0, and even we might want to find out if the derivative is undefined. So let's find out first when the derivative is equal to 0. To solve this equation, you need to be thinking about what type of equation this is. This is an x squared equation, oftentimes called a quadratic equation, and there's different ways to solve a quadratic equation. Sometimes you can do factoring. Factoring doesn't work with all quadratic equations, but you can try factoring. Sometimes it works. You can use a quadratic formula. That also works all the time, by the way. You could use other methods to solve this, but I've made some of these first problems sort of flexible so that this one can be solved using factoring. It can be solved using the quadratic formula or any other kind of technique that you are kind of trained in solving x squared type of equations. So I'm going to do the factoring just so we can see that and practice that, since I set it up so it can be factored. First of all, I'm going to factor out something common, which is a 3. So I get 0 is equal to 3 as a common factor. And then I'm left inside with x squared minus 6x and minus 7. And then I'm going to factor this trinomial inside. So 0 is equal to this 3. And on the inside, I'm going to have x minus 7 and x plus 1. And please double check that that's correct. Factoring is a guess and check prospect. So you should always sort of think about, is it really equivalent to x squared minus 6x minus 7? I'm not going to go through all that detail because I want to sort of stick to the main focus about analyzing these functions. So if we set things equal to 0, we have 3 things being multiplied. We have 3 times x minus 7 times x plus 1. So when we have a bunch of things multiplied equals 0, one of them has to be 0. So either 0 is equal to 3, which ain't going to happen, or we have something like x minus 7. 0 is equal to x minus 7. I guess I can put the 0 in either way, but I'm going to try to keep it lined up. Or we have 0 is equal to x plus 1. So one of those or more has to occur in order for the derivative to equal 0. And so we can see right here, this is x equals 7. And here we get x equals -1. So these two are important points. In fact, those are going to line up with this point right here. That's where x equals -1. And this point right down here, which is where x equals 7. So how do we find the y value for those x values that are important, those critical points? Well, we would like a formula which we could like plug in an x value and it would tell us the y value. In fact, that's the equation. The equation is the formula where you plug in the x number and you find the y number. And I can, of course, go over to my calculator like Desmos. I can make this into a table here. And I could just put in the number. Well, the -1 is already in there. So if I just get rid of this thing here, and then the other number I'm supposed to put in there is positive 7. So -1, let me get rid of the other stuff here, and positive 7. So this first critical point here, this first peak is at -1 comma 16. Boom. And the second one, which is off the screen, is at 7 comma -240. And what's really, really important more than these values is that we know that these sorts of local maxes and local minimums can only occur when the derivative is equal to 0 or the derivative is undefined. We found no other places where the derivative is 0. Oh, we need to look to see where they're undefined. But once we find all those things, we found all the possible maximums, minimums. Let's quickly find out when it is undefined. So we take this derivative equation, and you want to find out when it's undefined. When is the derivative undefined? Because it can switch from positive to negative, that as well. Okay, so when is it undefined? Well, we would have to have 3x squared minus 18x minus 21 is undefined. So here we have to rely on your knowledge of precalculus. This is a parabola, 3x squared minus 18x minus 21. There's no division by 0. There's no square roots of negative numbers. There's no logs or weird trig things. It's never undefined. So the way we look for things that are undefined, we look for the things that we can't do in math. We cannot divide by 0. We can't take square roots of negative numbers. We can't take a log of a negative number, etc. Right? So this is never undefined because we know that it doesn't have any of those possibilities where it's undefined. It's also a parabola. We know what parabolas look like. They're not undefined as well. So we've checked all the different possibilities, and we know that there are only two really important points called critical point, x equals 7, x equals -1, and we know what they are. We know that this one over here is a peak, and the one down there is a valley, and there are no more. I don't care how much you scroll around or look or whatever, you're not going to find any more. And I know that because I did the calculus, right? And that's the key thing I want you to take away from this is that we can stop having to guess. We can know for sure how many peaks, how many valleys, and things like that. As we do more of the chapter 4 material, we'll have more sophisticated tools for identifying these peaks and valleys, knowing ahead of time whether it's a peak or a valley or something else. The something else also has a name. It's called an inflection point. If you've ever heard that word before, we'll investigate what that means as well. So we're going to develop some tools so that we don't have to guess anymore about what a function looks like. We'll know all the important features. So that's kind of the idea here. Let's talk about increasing and decreasing. So we know that the graph is going to be increasing, decreasing at various points, and it switches or potentially is where the derivative is equal to 0. And the fact that these two are the places, the only places where the derivative is 0 or the derivative is undefined, those are the places where the graph could switch from a positive derivative, increasing, to a negative derivative, decreasing, or vice versa. The way I oftentimes help students visualize this, just make a number line. This is a number line for x, and then we're going to talk about the different x values where the derivative is positive and derivative is negative. So -1 and 7 break this x-axis into three different regions. So we have this region over here where x is less than -1. We have this region in the middle where x is between -1 and 7. And we have this region over here where x is bigger than 7. Because the graph can only switch from increasing to decreasing at one of these critical points, either where the derivative is 0 or the derivative is undefined, we know that it's not going to switch except at these important, critical points, these switching locations. So at -1 it could switch, at 7 it could switch, but once we know if the graph is increasing and decreasing in a particular area, then we know about that for the entire interval. And the easiest way is just to test. So let's take a number that is less than -1, and let's see if it's increasing or decreasing at that particular point. What tells you increasing or decreasing? The derivative tells us increasing or decreasing. So you can take any number you want. I'll just choose something like -2. That seems to be an easy number to plug in. And I'm going to take the derivative, and I'm going to plug in -2. And the derivative is this equation up here again. So it's 3 times -2 squared minus 18 times -2 minus 21. And what's that give me? That gives me, well, -2 squared is 4, so that's 4 times 3 is 12. A negative times a negative is a positive, so that's plus 36. And there's a minus 21. Now, I don't even need to know what this adds up to, but I do know it's a positive number. 12 and 36 is 48, minus 21 is, I don't know, I don't care. It's positive. This thing is greater than 0. Why do I only care whether it's positive or negative? Because we're trying to find out if the derivative is positive or negative. If the derivative is positive, then we know the graph is increasing. If the derivative is negative, we know the graph is decreasing. So at x equals -2, we have the derivative is greater than 0. So this is the derivative is greater than 0. So we call this increasing. And likewise, we can choose any point in the second interval between -1 and 7. A nice one might be to choose x equals 0, because that's a nice number to work with between -1 and 7. So we'll try x equals 0 over here. And where we're going to put it? Well, we're trying to see if it's increasing or decreasing. So we're going to put it into the derivative. So we find the derivative. We put in x equals 0. Remember, this is the derivative equation. And you stick in 0, so you get 3 times 0 squared minus 18 times 0 minus 21. And what does that give us? That gives us 0 minus 0 minus 21, which is negative. It's negative 21, but again, I just want to know what's positive or negative. So over here, we know that the derivative is negative. Dy dx is less than 0, so we call this decreasing. And then we would investigate some of them are bigger than 7, like 8, or maybe 10s is a nice number to work with, right? We could choose just an easy number to calculate, or I guess we could use our Desmos and just plug it in without having to do calculations. But I like doing this one by hand just so you can see what's going on. So for x equals 10, our derivative at x equals 10 would be 3 times 10 squared. I need some more space. 3 times 10 squared minus, is it 18? Yeah, I guess it's 18. Am I writing down the right derivative? Yeah, I am. I lost track because it's over here. 18x minus 21. All right. Minus 18 times our x value minus 21. And 10 squared is 100 times 3 is 300. Minus 180 minus 21. So this is greater than 0. $300 minus $180 minus $21 is greater than 0. So I know this last bit is going to be increasing. Over here, I'm running out of space. So this is increasing because it can it has a positive derivative there because the derivative is greater than 0. So understanding increasing, decreasing, understanding that you can easily find increasing, decreasing just by plugging a number into the derivative is going to be really helpful in doing some of the more sophisticated problems that we come across later in chapter 4. And once again, we can verify all this. We can look at the graph we had before, and you can see here on the left-hand side for the x values like -2 and all the values that are less than -1, the graph is increasing. And for the values between -1 and, or I guess 7 down here, between the valley down here. So all the values there, the graph is decreasing, and then after 7, the graph is increasing again. So the graph can confirm all the stuff we're doing here by hand. Okay, so that's the first sort of introduction to the idea behind local max, local min, more specifically about how we search for local maxes and local mins. We essentially kind of look to see when the derivative is 0 or the derivative is undefined. And those give us possible locations where it switches from increasing to decreasing, and therefore gives us an idea of where the local mins and local maxes are. We'll get a little bit more into identifying or classifying local mins and local maxes without actually having to rely on a lot of calculation. But we're going to take one step at a time, and I just want to make sure you get the idea of that straight away. So a little vocabulary check here. A peak point is called a local maximum. It means in that local area, the graph is as high as possible, and local minimum is the same idea. The reason why we use local is if you go back to this graph, there's my local maximum, there's my peak, but the graph certainly goes higher than that. I mean, the y value here is 16, but the y value here is definitely higher than 16. So it's not the global maximum, it's a local maximum. Right, so it's called absolute max in math terms, but we want to call it local. So in this area here, that's the highest, that's the peak. So that's the vocabulary that we use. All right, let's do a couple more examples, and then we'll be done with this video. All right, so my next example here, let me zoom in a little bit so it's easier to see. We have x to the 4th over 4 minus 8x squared. And we're going to be trying to find any local maximums and minimums and increasing and decreasing, etc. Okay, so strategy, we're going to be trying to find out when the derivative is equal to 0, or possibly undefined. So we're going to find the derivative, dy dx. The 1/4 doesn't affect derivatives because it's multiplied. Neither does the 8. I'll just do a little simplification here. This is x cubed minus 16x. Then I will find out when the derivative is equal to 0. And also try to find when the derivative is undefined. So derivative equaling 0 means that we have to have this equation, this derivative equation, equal to 0. Again, I'm trying to make these easier to factor and such for these first problems, so we don't get too stuck in the algebra, so that it'll be easier to sort of follow the train of logic without getting sidetracked on all of the nitty-gritty algebra solving for x and stuff like that. So here, when I factor this thing, I have 3 things that could equal 0. The first thing equals 0, or the second thing equals 0, or the last thing equals 0. Because as we know, when you multiply a bunch of things together and the result is 0, one of those things had to be 0. Could be more than one. In this case, we have x equaling 0, or x equaling 4, or x equaling -4. So those are important points. They're critical points. Let's find out when the derivative is undefined. So we want to find out when the derivative, which is x cubed minus 16x, is undefined. And do we divide by 0? No. Do we take the square root of a negative number? No. Do we take the log of a negative number or 0? No. Do we take the tangent of pi over 2? No. Why am I listing these things? Because there's only a few things in math which are just not computable, that we can't actually compute. Division by 0 is the most common, happens more often than these other things. But this is just a normal x cubed equation. And going back to your pre-calculus, you know the x cubed equations, they just kind of go up and down. There's no weird things that are happening. It's not undefined. There's no breaks. There's no discontinuities or anything like that. It is never undefined. It is never undefined. Which is, mostly the case that these derivative functions are undefined, but you do have to check. All right, so we have 3 important points, critical points. I'm just going to make a little number line. 0, 4, and -4. That's going to break our number line. This is our x-axis here. It's going to break our number line into 4 regions. The region that's less than -4, the one between 0 and -4, the one between 0 and +4, and the one greater than 4. And I'm going to be plugging in values of x in each of these intervals, each of these regions, to see whether it's increasing or decreasing. So I plug them into the derivative equation because the derivative equation tells me increasing and decreasing. The original function tells you y values. It doesn't tell you increasing or decreasing. And the derivative function does not tell you y values. It only tells you increasing, decreasing, tells you the slope, right? So we're going to have to make sure to plug it into the right equation. Maybe what I'll do is I'll just make it easier by making a Desmos table here of x cubed minus 16x so that I don't have to do all the calculations by hand. Let's see. Can I sneak in something in here? Let's see if I can do that. Yeah, there we go. So y equals, I have to go back and look at this thing, x cubed minus 16x. Y equals x cubed minus 16x. And I don't really want that graph, I just want the table. So that's my derivative equation. And I'll go to this little thing here and I say, I want to make this thing into a table. So I make that a table. And then the values, just to remind you, are 0, 4, and -4. So I need not to plug in 0, 4, and -4. I mean, if I do, I'll show you what I get. If I plug in 0, I get 0. That there says that the derivative, remember, we're putting the derivative here, derivative is 0. What about at 4? 0. What about -4? 0. This shouldn't be surprising because that's how we found 0, 4, and -4. We found them by making sure that's where the derivative is equal to 0. Where this equation is equal to 0 are those 3 points. So yes, you can plug in those numbers, but they don't really tell you anything. We need to plug in numbers somewhere in those intervals. Like over here, we could plug in -5. Here, we could plug in -3 or -2 or -1 or -1.72. I'll plug in -1 just because it's a simple number. I'll choose any number over here, like +1 or +2, something like that. And over here, I'll choose something like +5. So you have to pick a number in each of those regions and find out whether the derivative is positive or the derivative is negative. All right, so I guess I keep those. We're going to do a -5, a -1, +1, and +5. So those are representatives of those 4 regions. So at -5, the derivative value, remember this is the derivative is -45. At -1, it's positive, so the derivative is positive, increasing. Then it's decreasing, and so it's switching between decreasing, increasing, decreasing, increasing. So this here is decreasing, increasing, decreasing, increasing. So we know that -4, 0, and 4 are where the graph switches between decreasing and increasing or increasing and decreasing, and those are the local max and local min. I can identify them without actually using a picture. We do actually can get a picture real easily, but think about this. If you have a graph which is decreasing, it's going down. If it then increases and going up, what type of local min or local max is that going to be? It's decreasing and then it's increasing. That's got to be a minimum, right? Because it's going down and then coming up. So this one here has got to be a minimum. what about the next interval? In the next interval, it's increasing and then it's decreasing. So increasing, and then it hits when x equals 0, and then it decreases. That's got to be a local max, right? Because increase and decreasing has got to be a local max. And similarly, we have decrease and increasing. So this last one over here has to be a local minimum. And we can verify that on the picture. So let me go to the picture, get rid of this old example. And is that true? Oh, no. Okay, let me not get confused. Oh, here we go. Is it x to the 4th over 4 minus 8x squared? Yeah, that's the one right here. X to the 4th over 4 minus 8x squared. Okay, so that's this one right here. I'll turn that on, turn this off. And this graph looks sort of like a W. Get rid of that little dot there too. Okay, so this is my graph of like a W thing. It has a local maximum at x equals 0 right here, has a local minimum at x equals -4, and a local maximum at x equals +4. So that can be verified here on the graph. And there are no other maximums or minimums anywhere. It just keeps going on. How do I know that? Well, I would have found more critical points. I would have found more places where it switches. If the math gave me more, if there were more places, I'd find them already because I did the math. I set the derivative equals 0. I set the derivative to be undefined, and that's all I got. So there's only 3 places where it can possibly switch. All right. One last problem here, and then we're going to be done for this video. So just another example. I have example C here. Y equals x to the 2/3 minus 4. Again, feel free to stop the video at any time if you're thinking you got an idea and want to sort of practice and see if you can figure out the steps and make sure you know them all. It's a great time to do so. And then you can know for sure if you got the whole thing down, or if you get stuck, you can know how to get unstuck when you watch my solution. Okay, so if you did go and try that, nicely done, and welcome back. And now I'll do my answer for example C. So again, we're just trying to do the same thing: local max, local min, increasing, decreasing. So I'm going to find the derivative. Dy dx, or y prime if you like that. The derivative of x to the 2/3 is 2/3 x to the -1/3, and the derivative of -4, well, it's just 0. So it's just that right there. So we need to find out when the derivative is equal to 0, or possibly when the derivative is undefined. So I will set this equation equal to 0. The derivative equation is 2/3 x to the -1/3. And I certainly get rid of the 2/3 by multiplying both sides by 3/2. And that would be x to the -1/3 is equal to 0. Right? You get rid of numbers just by multiplying on both sides, but 0 times any number is still 0. So I still have this x to the -1/3 is equal to 0. So is 0 raised to the -1/3 0? It actually is not, because the negative exponent really means reciprocal. So this really means 1 over x to the 1/3 is equal to 0. And you can't divide by 0, my friends. So x equals 0 is not a solution. In fact, there's no solution to this. I can multiply both sides by x to the 1/3 to clear the denominator. Just like I got rid of a constant, I can get rid of functions this way, or x's this way. And then with x to the 1/3 divided by x to the 3rd is 1. And 1 equaling 0 has no solutions. So when I solve this equal to 0, I got no solutions. Which is a little bit different than the last one. But if you remembered what we talked about before, or if you went ahead and solved this thing and you realized that x equals 0 is not a solution because you're dividing by 0, that may have given you a hint about this second part. Remember, we're supposed to find out when the derivative is undefined. So let's find out when this thing is undefined. 2/3 x to the -1/3 undefined. And let's just write this in its fraction form, just so it's easier for some folks to see. Negative exponents are reciprocals. So is this possibly undefined? And the answer is yes. Yes. We do have a division. We divide by 0 when x is equal to 0. Remember, that's kind of what we were talking about when trying to find out when the derivative is equal to 0. So if you got this equation and you found out x equals 0 was a solution, actually algebraically that wasn't correct, but you did find the right critical point, because it turns out when x equals 0, the derivative is undefined, and that's another example of how we find, that's the other way we find critical points. So there's only one critical point. There's only one thing to investigate here. That's x equaling 0. That happens officially when the derivative is undefined. And we can make a little number line. We can put our x equals 0 here, this x-axis. It breaks it up into two regions. So we know increase and decreasing can only possibly switch at that one location at x equals 0. So we can investigate something like at -1 or +1 or any other number you choose, and figure out whether it's increasing and decreasing. So how do you determine increase and decreasing? Use the derivative. So you take the derivative, you plug in -1, the derivative equation's over here. So this is 2/3 -1 to the -1/3. -1 to the -1/3 is -1. So we get -2/3, and this is a negative derivative. So this is decreasing over here on the left-hand side. Let me not put a mark here because it looks like I'm breaking it up into more regions. Okay, there's only two regions, stuff to the left of 0 and stuff to the right of 0. All right, so let me just get a little bit more space. And we'll find out when the derivative is +1. You may already see what that is. X equaling +1. And that's going to be 2/3 +1 to the -1/3. +1 to the -1/3 is +1. So you get a +2/3, and this is increasing. So you have a decreasing, then we hit 0, which is an important point, and then you have increasing. So what kind of graph decreases, has something important, and then increases? And that's a minimum. That's a local minimum. So this right here, it's decreasing, then it's increasing. So that point right there is a local min, and that's x equals 0. How do you find the y value? Well, you plug it into the original equation. The y equals equation tells you y values. So you could plug in x equaling 0 into this original equation if you want to find the y value. You might already see that the y value is -4, but let's go check it out on our graphing. So let me get rid of this picture here. And here it is, x to the 2/3 -4. So there's our picture. I can zoom in a little bit. It has this important point at 0. It comes to a point right there. It's not really like smooth. It's not really where the derivative is 0. It's actually where the derivative is undefined. And that's going to be our local minimum. I did prepare one more graph over here to show you another example of where the graph comes to a point where here we have increasing on the left-hand side, decreasing on the right-hand side, and where it switches, in this case, is a local maximum. So you do really need to check when the derivative is undefined, because you do have some examples like these two guys where you will have a switching point, which is a local min or local max. That's not where the derivative is equal to 0. It actually happens where the derivative is undefined. All right, so just quick vocabulary check. Zoom out a little bit here. If you can see this bottom part through all my scribbles, some point, an xy point where the derivative is equal to 0 or where the derivative is undefined. So these two possibilities, that is called an inflection, or called a critical point. So critical points are when the derivative is equal to 0 or the derivative is undefined. The x value is called the critical value. They almost make them interchangeable. I'm just trying to clarify some vocabulary in case it sounds confusing at some point to you folks. All right, so our general strategy that we're going to pick up in our next video is we're going to try to find the critical points among other important features. And we should also use the fact that if it has a local max or a local min, it must occur at a critical point. And why is that? Because the only way it can change from a positive or increasing derivative to a negative, a decreasing derivative, is to go through 0 or have some undefined feature where it goes to that. So it can't go from positive to negative without going through 0 or being undefined at some location. All right, so hopefully you found that video helpful and useful, and please reach out if you have any questions or want some more examples or anything of the like. And I hope you have an enjoyable day.